Okay, so hi everyone. This is Let's Discuss a Paper right after reading it. And in this journal club, we pick it up and started reading one paper 2 hours ago, and then from now we're going to discuss the paper. Today we have two people, Changshen and me. Changshen, can you introduce yourself?
Okay, hello everyone. My name is Qian Chen, and I'm currently a PhD student at Monash University, Australia.
Thank you. And me, Yota Kawashima. I am a research engineer in Japan. And today we are going to read a paper published in Nature Communications this year, 2023, March. And the title is Intrinsic Timescales in the Visual Cortex Change with Selective Attention and Reflect Spatial Connectivity by Roxana Zerati et al. And before starting the discussion part, I will first give you just a quick summary. But before that, this part is a little bit long for me and was a little bit complicated to understand. So I might misunderstand this paper. And I hope Changshen correct me, but we'll see. Anyway, so this paper, as the title says, interested in intrinsic timescales. And as you might know that, of course, that different brain areas has a different functions, and the temporal dynamics of each brain area seems to different. So, for example, sensory area tends to have a faster dynamics than the more higher area, such as prefrontal cortex, which are related to some cognitive functions. And one way to characterize that kind of temporal dynamics is called intrinsic timescale, which is defined by a trial-by-trial autocorrelations. And of course, when we use that measure to characterize the brain activity in different brain regions, we have faster versus slower depending on the area. But it is less known how it changed in a single area. In this paper, focusing on visual area, depending on different task conditions. And also the question what this paper tried to answer is that what is the physical mechanism to generate such kind of differences in timescales? So in order to answer this question, again, this paper focused on visual area during attention manipulation task. And this paper recalled spiking activity from macaque before during spatial attention task. And then first confirmed that they saw two different timescales in the V4, first and slow timescales. And then try to explain what kind of an underlying mechanism generate the time scales with computational models. So what they had three different task conditions. One is just a fixation task without attention manipulation. And the other one is the detection of a change of orientation of rating with and without spatial attention. And the other one is to detect the luminance, the change of luminance with and without attentions. But anyway, so again, they saw that the first two different time scales in B4, and then they found that slow time scales changed between with versus without spatial attention to the receptive field, the corresponding receptive field of that V4 area. And also they found that the slow timescales are correlated with the reaction time under the attention conditions. And that's basically the empirical or observed result from the experiment and the recording. And in order to explain these observations, they used computational models. And then they tried three different models, but they found that the model with spatially kind of well connected networks can explain the observation, but just randomly corrected neurons with two different, for example, cell types cannot explain the observed data. And also by changing the network connectivity, specifically change in the efficacy. So here, I think what they mean by that is how likely one neuron to fires. So the high probability means more efficient, I think. And then that changes capture the change in the slow time scales. And this may be the explanation of why we see the change in slow time scales under attention conditions. And this is my summary of this paper. And Chanshin, do you want to add anything?
Yes. So so first, one thing to highlight is that the spatial connectivity model they developed was specifically about how nearby neurons are connected to each other, and they will have recurrent dynamics among them. And I think the recurrent dynamics is very important because it was the recurrent dynamic that modulate the slower timescales. I think that's what they found. And another thing is the efficacy. I'm not sure if I understand your explanation correctly, but my understanding to efficacy is like how many nearby units can a unit activate when it itself is excitatory. So they have this critical point of 1. I think like default is 1 unit activates the other, but it can be increased in a sense that 1 unit activates more than 1 or decrease, which I don't know. Maybe they just activate themselves without influencing anyone else. Something like that.
Okay, yeah, I agree with your explanation. So I kind of skipped that part. I mean, so they had 2 parameters. One is self-excitation. So this kind of, describes or represents how single neuron can fire by itself.
Yeah.
And the other one is the recurrent interactions. And this is the key, I think. And that is something I skipped in the summary. So yeah, thank you for pointing that out. So yeah, but anyway, so do you have anything to add, or is that basically it?
No. Let me see. I don't have anything else to add.
Okay, so let's move on to the discussion. So first, or just a question, any clarification question is fine if you have.
Yeah, I have a question on terminology. What is the difference between correlation and autocorrelation?
Okay. So yeah, they have, autocorrelation and cross correlations, right?
Yeah.
And autocorrelation is the correlation within single time time series. So we have this, time series. Anything is fine. So x-axis is time and y-axis is I think in this case is the not y-axis, but just whether it's spike or not, or in the case of brain activity, it's just an amplitude. And then that in order to compute correlation, we need a kind of 2 points, right? So x-axis, y-axis, and just plot the dot and then take the correlation. And here we set the time lag. So we have 1 point from, for example, 0 millisecond. And then we have another point, for example, 1 millisecond ahead. And then we will have 1 point based on these two values, right? 0 and 1 millisecond from single time series. And then we shift that +1 millisecond. And then we will have another point here, 1 millisecond, 2 millisecond. And that can be plotted again in the 2D coordinate as a single dot. So
like mean within each time window?
So I think it's better to explain with note, and I think it will help. But I don't know how. I forgot how to. Does this have?
I think it does.
Not.
But
advanced share options. No.
I don't think so. But I'm not. Hey, wait, hang on.
Yeah, because if I share a screen now, I think I will share the the screen with the paper, which I want to avoid. Advanced sharing options.
yeah, you need to share screen first. Do you need to share? Someone needs to share the screen first before we can do any.
Okay, so let's. Yeah, no, I found it. So this is x-axis time, y-axis something. For example, voltage. In the case of time, now brain activity, and we will have this kind of brain activity, right? It's from single trials. And then we set the time lag t value or tau. This is time lag. And then first we will pick the data from here, 0 millisecond, and then 1 millisecond, if this tau is 1. And by doing that, here is the, for example, t, and then the other is t plus tau. And as we start at 0, t equals 0, we have first dot, right? And this is 0 millisecond voltage, and this y-axis is 1 millisecond. Again, here tau is 1, right? And then next we shift this way, and then we will have another dot, right? And then we can plot like this, and then we can compute the correlations.
I see.
Yeah, and then this tau value is important because if this value or if we change this value from 1 to, for example, 100 milliseconds, and then if we see much higher correlations, then it means like, okay, this time series seems to kind of repeat the same, pattern for each 100 milliseconds. Something like that. That's autocorrelation. But again, this is just my understanding and my wrong. But the procedure is I think, should be correct. From single trial, we want to compute correlations. So we introduce this time lag parameter tau, and then just take correlation by plotting this way. And this is autocorrelations, and the standard cross correlation is, instead of thinking the correlation from single trial, we have two trials, or maybe two channels, two brain areas, and then we pick the same the data point from the same time, 0.0 millisecond, and then plot the data in 2D matrix. And in this case, x-axis is channel 1, and then the other axis is channel 2. And then we can plot this. And then if we found a high correlation, then it means that these two channels have some kind of interactions or synchronization or something.
Okay, thanks.
Okay.
Cross correlation, I understand. So to verify my understanding to autocorrelation. So if we have a low autocorrelation, then that means from first t to t plus tau, we have 1 point. And if that kind of excitatory activity decays very quickly, like in the next time window already, then we'll have another point which is kind of very far from the previous point or something like that. So the faster the excitatory activity decays, the lower autocorrelation you get. Is it something like that?
I think yes, I think. I think. So I have not analyzed the spiking data, so I don't know how to interpret. But in terms of the brain activity, if we have, pure sine wave like this, then we will have a highest autocorrelation when the tau is this length. Because we will have the exact same, trend from here to here and from here to here. So the data will be like this.
Oh.
Because here 0, here 0, and then the next step, here 1, here 1, and then 0, 1, 2, 2, 2. Again, once it reaches the peak, and then we come back to 0 again, which corresponds to here. And then next to the negative part, and then reach to the negative part, and then coming back to the positive part again. And if we change this tau value, let's say not this, but here, then the trend will be different. First start 0. But here, if we take this value, 1, the next here is -1. So we have this point, and then next 2, and then here -2. So B. So we will have this line. So here the correlation 1, here the correlation is -1. So based on this value, we can say, okay, this seems to repeat the same pattern with this time not time lag. Yeah. Not this time lag, because we see high correlation here. Does it make sense?
Okay, maybe just summarize what you can do is better for me to understand. Sorry.
I think my explanation is not good, so it's better to check Wikipedia. That's first.
I understand. I probably understand like 60% of it. I'm just trying to think about what does high autocorrelation tells you and what low correlation tells you. I feel like, is it if you have a high autocorrelation, it seems to mean that it takes longer time for like this to.
Yeah.
If it's low autocorrelation, then it's like within a short time they're doing this.
One other explanation can be, I introduced the tau value, right? The time delay. So it can be interpreted that, the self connection in a sense with the delay. So for example, one neuron activates at time t, and then each neuron has a self connections, and that will the activation at time t will contribute to the activation status at the t plus tau. Kind of.
I see.
And that kind again, explains the temporal dynamics.
I see.
But sorry, again, my explanation can be wrong, so it's better to check by yourself. And I kind of but I think I hope it's correct. So anyway, so the message from this autocorrelation is just compute the correlation from single trials, not across channels or across trials. And then for that, we need to introduce this time lag tau value, and that time value capture the property of temporal dynamics. That's the I think the key point.
Okay.
Yeah. Anyway, so other questions? If not, I have one kind of not question, but comments. So when I, read the paper on the introduction part, they introduced first intrinsic timescales, and after that they introduced task-induced timescale. And I guess it's different from intrinsic timescale from stimulus-driven activity, because it's kind of complicated and maybe so here in this study they only investigated intrinsic timescale, right? And then intrinsic timescale, they compute the timescale when monkey didn't see any stimulus, only background gray screen. That's spontaneous activity.
Yeah, when they're looking at just fixation.
Yeah. And then when they present stimuli to the monkey, they still compute the intrinsic timescales. But for stimulus driven activity. So
yeah,
go ahead. Complicated. It's complicated because they introduced this task induced timescales in the introduction, but they did not investigate that on the intrinsic timescale. And my understanding is that this intrinsic timescales is just trial by trial autocorrelations. So we can compute the timescale for single trial, but task-induced timescales, according to their introduction, is average across trials. I don't know at which point they take the average, but take average across trials first and then maybe compute the autocorrelations. That's the task-induced timescales. And intrinsic timescale is autocorrelation for single trial, but I don't know what kind of difference that makes. I mean, they introduced in the introduction, they say that seems capture different properties or different temporal dynamics and seems to have different underlying mechanism. But I think, this is maybe just too minor, and I should not, raise this, but I just wanted to, check whether my understanding is correct or not. Or did you have that confusion or no?
Actually, yes, I also have that confusion, but it did not arise until you talk about intrinsic timescale is trial by trial. And then I realized I did not understand intrinsic timescales and the task-induced timescales correctly, because I thought task-induced timescale was the trial by trial one, because it makes sense, right? When you're in a trial, you have task-induced timescale, but turns out task-induced timescales comes from averaging all your responses, like neural activities, across the entire task. But then the intrinsic timescale dynamics vary substantially across trials. I didn't understand that. Also, this is probably a terminology issue, but if it varies trial by trial in a cognitive task, how is that intrinsic? I thought intrinsic would be something that is like something persistent in the background. But this is even more minor than
intrinsic. What they mean is, I don't know. I don't know. Just terminology, confusing terminology, and that's I think.
How is intrinsic timescales? Intrinsic is my confusion the whole time, because they said, oh, intrinsic timescales varies across trials, and these changes are predictive of reaction time in decision-making tasks. Then I feel like it's very different from some terms that has been similar terms like default mode. When you say default mode, then this network is always there when you are idle, right? It doesn't really do this kind of very well, as far as I know, they don't really do like, oh, it varies across this and that, and that's why it's called default mode.
So I guess instead of saying intrinsic timescale, just saying autocorrelation is better.
Yeah. Yeah, otherwise I guess the intrinsic part about this is it concerns single time series or single neuron. And then it becomes more confusing when it talks about the connectivity between neurons would explain their intrinsic timescales, but not the biophysical properties of single neurons. The single neurons autocorrelation is not explained by its own, but it's explained by its relationship to the others, to nearby. Yeah, that's.
Yeah. I think just, yeah. But yeah, anyway, that I think just terminology, complicated terminology, and that's not, author's fault, I think, because
Yeah, of course,
other
of course.
people just use that term, so they have to use that, and that's it.
Yeah.
Yeah. But yeah. Yeah.
I have another confusion, but I'm not sure whether I should bring this up, but in their models, their first model, which is the one with the spatial connectivity, they talk about this model actually predicts a mixture of multiple slower timescales, but not one slower timescale, which is odd because their first finding was there are two timescales, one fast and one slow, right? But then in the model, in building a model to understand the slow timescales, they built a model that predicts multiple slow timescales. I don't know why. And maybe interaction timescale is something different from this, just the slower timescale they've been talking about in their first results. But I don't fully understand this part.
Okay. I didn't pay attention to that, so I didn't notice that. So I just can't say anything, but I guess what they mean is that the slow time scales changes, but can change in this model. And then therefore, attention, and that's kind of capture the changing slow time scales in attention conditions.
Oh, I get it. By tuning the connectivity, you change the length, the length of the slower time scale, hence modulating, which adapt to the attention conditions, different attention conditions. Oh, okay, I understand.
So I think this model takes the connectivity and then compute this time scales. And then, but in reality, I think what's happening in brain is this connectivity change during task. I'm not sure whether it's really happening or not, but their expectation is that it changes, and therefore, during attention condition, the time lag or time scales changes. Yeah, so that part I don't know, how fast or how quickly, how often, neuron change its connectivity or efficacy, because it's single trial, right? Attention conditions. How quick or across trials maybe, because in one condition you pay attention. Wait. No.
In one area you pay attention, the other area you don't.
Yeah. So yeah. Yeah, I'm not sure how quick the brain change its connectivity. Yeah, of course it changed, but I'm not sure the time scales. We know that, relatively long span, the time scale. When I say long, means like a day or a month, years. Yeah, sure, it changed, of course. But here, the change should be, occur at least within hour or minutes long, maybe second, right?
If you look at figure 2C,
yeah,
the time scale for tau2, I think tau2 is for the recurrent. Oh no, tau2 is for tau2 is for 2 time scale model. So it ranges between around like 10 milliseconds all the way up to like above 400 for stimulus driven activity. So that's the time scale alone. And as it's most likely modulated by connectivity, then connectivity can change. I mean, in the end, connectivity here, I think it's just what they're saying is, what's it called? Functional. Is it something like functional connectivity? Where basically it's just how many neurons can one neuron activate, right? It's not like across area, that kind of long projections.
So I now, realize that they, discussed about this in discussion.
They talk about this in discussion.
Yeah, mechanism for attentional moderation of time scales. It's page 10. And sorry, I did not have enough time to read this part in detail, so I can't. But they just list a possible mechanism for to explain that quick change in not structure, connectivity in network. Yeah, but I don't know. Adaptation can be quick, but not. Well, but yeah. Anyway, that's another comments. Question.
We read another paper about, it's probably not time scales, but it's also related to connectivity, recurrent connectivity associated with attentional modulation. We read the other paper, right? That one was also very difficult. It's also on V4. I remember it's like V4 recurrent connectivity.
Was it monkey as well? Maybe native.
Yeah, it's also monkey. Yeah.
Yeah,
and that's between V4 and V1. I mean, so if they can do that between V4 and V1, then they can probably do this within a unit of 8 nearby neurons.
But their claim, but I don't know, is that we can see these changes in local network, right? So, and also in the paper we read before, they check the attentional modulation in V1 by V4, right? So what changes is the activity being in V1, but here they are talking about the activity in V4. So I don't know how these two different papers or findings can be interpreted, although they are both of them talking about attentions. I don't know whether the previous paper, the paper we read before, moderated spatial attention or not. But I guess it's monkey, so we can't do any complicated attention manipulations like human. So maybe it's spatial attentions.
But I guess the take-home message between these two papers kind of overlap in a sense that in both locally, which is suggested by this paper, and globally, as suggested by that other one, the recurrent connectivity seems to matter for attentional modulation. So when there is attention, there's recurrent activity on both a more global level between areas and local level down to a cluster of neurons.
Hey, yeah, great summary. Great summary, or yeah, great point. If or any other question, comments? I think your, the not summary, the final remark was the good, to finish this discussion. So
yeah,
let's finish. Okay, then see you next week. Bye bye.